Hey everybody, it's Dr. D. I'm back talking to you about hypothesis testing for tests of two means when we don't know the population standard deviations. And today what I want to do is I want to walk through an Excel example with you so that you can see how some of these calculations are going to be done in practice. Let's see, without further ado, let's take a look at the example we have in Excel right here. From problem set 5, number 4. Periodically, Merrill Lynch customers are asked to evaluate Merrill Lynch financial consultants and services. Higher ratings on the client satisfaction survey indicate better service, with 7 being the maximum service rating. Independent samples of service ratings for 2 financial consultants are summarized here. Consultant A has 10 years of experience, whereas Consultant B has 1 year of experience. Use alpha equals 0.05 and test to see whether the consultant with more experience has the higher population mean service rating. Let customers of Consultant A be population 1. And then here you see the data drawn from Consultant A and Consultant B. If you look at the question, they say state the null and alternative hypothesis, compute the value of the test statistic, what is the p-value, what is your conclusion. So pretty straightforward. It's just asking us to run this test. I do want to draw attention to the language here in that you can see that one of the things I've kind of been digging into is that we've got two populations that are different in some observable way, which is to say one of them has more experience than the other. And then the question is, are they also different in some difficult to observe kind of way, which is, are their customers more satisfied? And so that's what they want to know. Test to see whether the consultant with more experience has the higher population mean service rating. So let's take a look. The consultant with more experience is Consultant A. And so they want to know, is it the case, can we show that, right? So if it says test to see whether, that means the HA is, that is what's about to be presented. Test to see whether the score on average in the entire population for A is higher than, has higher population mean service rating than Consultant B. And then it said, let customers of Consultant A be population 1. So this turns into HA mu1 greater than mu2. Now we want to turn this into a test of the difference between two means, and we do that because that will spit out on the other side our hypothesized difference, right, between the two means. So in order to do that, we need to get these two together on the same side. I'm going to subtract mu2 from both sides, and if I do that, we should get the alternative that we're looking for. Get HA mu1 minus mu2 is greater than 0. The null hypothesis that corresponds has the same form, but it has the opposite binary relation, right? Because we need those to be mutually exclusive and exhaustive. So mu1 minus mu2 is less than or equal to 0. So those are the alternative, the null and the alternative hypothesis that we're going to be choosing from. And if we go in here into these drop boxes, there's a lot of confusing symbols, but some of them are the ones that we need. There's H0. Mu1 minus mu2 is right there. I'm going to copy that again. This is a greater than sign. This should be 0. And then let's see. It says check carefully because it didn't finish. Less than or equal to. There it is. Sure enough, that's correct. Right. So that's our mu1 or our H0 and our HA. All right. It says compute the value of the test statistic next, but you and I both know that we'll be skipping a step there. This was the end of step 1. Step 2 is to choose a level of significance, right? So we got to choose our alpha. And our alpha is going to be given in here somewhere, I think. What is your conclusion? It says use alpha equals 0.05, so it's given right up there in the text. So I want to make sure we get that down for later, and I'll type it in here too. Alpha 0.05. Okay. Now step 3 is to choose a test statistic, which clearly we have to do before we compute it. And in order to do that, what we've seen so far is we have a test of two means, right? So on our previous lesson, we learned that if we go in this direction, we're testing two means, and we're either going to know sigmas or we're going to have s's. Let's see. Do we see up here what kind of standard deviations? It says S right here. It could say sample standard deviation, etc. But this data came from the samples, and so we're in a situation where we are dealing with sample standard deviations. Our sigmas are unknown. So we go this way, and then down here on the decision tree. And if you recall, that yields the following test statistic. T equals x bar 1 minus x bar 2 minus d0 over square root of s1 squared over n1 plus s2 squared over n2. And if the null is true, this will have a t distribution. And that t distribution has a number of degrees of freedom. That makes for a kind of a complicated formula. I'm going to write it now just so we have it down for later. I may copy and paste it as we move. But it's s1 squared over n1 plus s2 squared over n2, that quantity squared, over 1 over n1 minus 1 times s1 squared over n1, that quantity squared, plus 1 over n2 minus 1 times s2 squared over n2, that quantity squared, rounded down. Right, so once we find this fraction, we round it down. And I want to draw your attention real quick, just we do have pretty small sample sizes, 16 and 10. The t distribution has pretty nice properties even with small sample sizes, so that's one of its nice features. All right, so first things first, we need to find the value of this test statistic. And to do that, we're going to need our, I'll pull them down from above so we can see them as we go. We're going to need S bars, we're going to need S's, we're going to need N's. We're going to need S squared divided by N's, and we can pull those down. So X bars right here. And I'm just bringing these down by copying and pasting. That's just the data that the question gave us. And now S squared divided by N is going to be this number right here divided by this number. Order of operations means we don't need to worry about parentheses in this case. That should give us the right value. And then I'm just going to use that same formula right here, right, where I'm just taking the S squared and dividing it by the N. Now, to get my T numerator, oh, I also need D0. Our D0 comes from these hypotheses, so that's right there. My T numerator, yeah, D0, right? So I just want to rush past that. That's just that number that's in your hypotheses. That's D0. Okay, so now I think I have all the pieces that I need. I just need to do addition, subtraction, and some square rooting. So our T numerator is going to be our X bar 1 minus our X bar 2 minus our D0, which is just 0 right there. We could put parentheses in if we want. You can see it's not going to have any effect here. And so there's a 0.57 customer satisfaction point difference. Our variance, which is just the sum of these two S squared N's. Here, let me give you this formula. Have it if you want to pause. Our variance is S is just the value right here, right? Is these two things added together. Squared over n1 plus s2 squared over n2. Not sure what I did wrong there, but yep, those things added together, that's what I'm looking for. Again, there's the formula for you if you want it. And then to get my t denominator, or my standard error, I just need to take the square root of that. So square root of this value right here. So to calculate my t statistic, I now have gotten myself to t equals 0.57 divided by 0.286. That's what I'm trying to find here for my t. That should be the value right here. Actually, I'll do it separately just so I have it labeled. T denom. It should be a t-score of, yep, 1.9923. There we go. How many decimals do you need? Probably not 4. I think that overstates how precise we really can be. I'll stick with 1.992. But there we go. That's the value of our t statistic. And that is the end of step 3, right? We've calculated the value of our, we've computed our test statistic, collected all the data. Or sorry, that's the end of step 4, I should say, right? Step 4 is to actually compute this. Step 5, as is always the case with hypothesis tests, step 5, we're going to find a p-value and then draw a conclusion. To find a p-value, what we need to do is we need to find an area under a curve, right? So we've got a t-curve, and that's centered at 0. It's symmetrical, as always. And we've got a test statistic, which is 1.992. And then according to this set of tests, we've got a greater than sign in the alternative, which turns itself into an arrow pointing right. So our p-value is going to be the area in the right tail over here. This is our p-value. In order to find that, though, we need to know how many degrees of freedom we have in our curve. We're not going to be able to use the formulas in Excel to find that unless unless we can draw down the degrees of freedom, plug that in. So we're going to need the formula we had right here to find that. And I am going to copy it, I think, because I may want to update it numerically as we move. So let's pull this down. It's a little ugly because I still have those fragments, but let's clear that stuff up. We're going to get this, and then we're going to round it down. So what do we have to do? Well, we got to calculate this. So just to be clear, some of this stuff is already done, right? So I mentioned this the last time we met, but the degrees of freedom is going to be this value right here in the numerator is this variance, right? So that's going to be 0.08185 squared. And then over here we've got 1 over 16 minus 1 times, and then this formula right here, which again looks like it requires squaring and then dividing, but we've already done it, is actually this 0.0256. 0.0256 squared plus 1 over 10 minus 1 times this right here, which is 0.05625 squared. Right? So you can see that it's not like, I don't know, most people's idea of a fun time, but it's not super difficult to figure out what that is. So let's see, if I wanted to get my degrees of freedom numerator, that's going to be this variance squared. And then I'm going to have my df denominator, but it's going to have a left side and a right side, right? So the left side and the right side here. Actually, let's do 1 divided by n minus 1. Do that first. 1 divided by n minus 1. If you do it right, you can take advantage of copying and pasting a little bit. So these are these two values. And then I'm going to be doing my s squared divided by n squared. That's this part right in here, right? And I got to do that on the left side and the right side, so I have to square this 0.0256. And then I have to square the 0.05625. And then I have to multiply them together, right? 1/15, which is 0.066667, times 0.000655. These are going to create some very small numbers, right? Because we're taking a fraction of a fraction. It might go into scientific notation, I'm not sure. But if it does, don't get too worried. So I'm just going to call this the product. We're going to have a left side and a right side. This number times this number. Sure enough, it did go into scientific notation. I'll copy and paste these so you can see them. And then I'll talk a little bit about scientific notation just as a brief refresher. So that 4.306, just so you know what that is, 907 E negative 0.05, or E negative 0.05, just means that you write this number down, and this E means you move the decimals, times 10 to the negative fifth. So you just go 1, 2, 3, 4, 5, 0, 0, 0, 0. So that's just 0.000043697. So it's just a number. It's just a way of writing a number in a way that lets you see it, see more of the relevant parts, because those leading zeros don't contain any informational content other than just how far away it is from a big number. It's a very tiny number. All right, so now I've got this part. That's this number right here. The other side over here is the 0.00035. Now to get my df denominator, I just have to add those two together. So that's this value. And then my degrees of freedom is just my degrees of freedom numerator divided by my degrees of freedom denominator. And I have 16.9497 degrees of freedom, which is to say 16, right? I'm not actually going to round it down. I know that it needs to be 16, and I'll show you. But I'd rather have Excel refer to a cell that I have here for my degrees of freedom. All right, now we learned earlier that we need to find the right tail of a t-distribution that we now know has 16 degrees of freedom. I'm going to find the area in the left tail first. Area in the left tail equals t.dist, and then my t statistic is right here. That's what it means by x. and then my degrees of freedom is right here, and then I want it to be cumulative. So that area in the left tail is going to be 0.9682. And now I need to subtract that from 1. I know it's going to be 0.0318, something ballpark there, but I think that, but I'll find it exactly with Excel. Area in right tail. Oh, let me give you the formula here. 1 minus this. Now I could have done it right away, right? One thing we learned in the last video is that there is a t.dist.rt formula. And if I do that and I just plug this value in and 16, it'll give me exactly the same value. If you want to learn more Excel formulas, you can do that. It always works to subtract from 1 to get the right tail if you just know the left tail formula, so that's fine either way. The other thing I mentioned is that we could round this down, or we're supposed to round it down, but Excel does it for you. If I change this to 16, you can see no numbers change. If I change it to 17, 0.001, they do change. But as long as it's 16, 16.5, 16.25, 16, none of that changes, because that is 16 degrees of freedom as far as Excel is concerned. All right, so right tail test, so the p-value should be the size of the right tail. Sure enough, that is correct. All right, so we're done with the first half of step 5, which is to compute the p-value. It's 3%. Now we have to draw the conclusion. Well, earlier we said that alpha was 0.05, right? That's this number right here. So if alpha is 0.05, and our solution, we said there's a 3% chance that you would see samples like this, what we can now say is that the p-value, which is 0.032, is less than alpha, which is 0.05. And if that's the case, then we reject the null and accept the alternative. I'm going to go down here. Got some drop boxes. Reject. And then the thing I'm rejecting is the null. And there it is. We're correct. Okay. So that is an example of how to use Excel to calculate, to run a hypothesis test, to calculate a test statistic and a p-value, and then to draw a conclusion for a test of two means where the population standard deviations are unknown. I hope you found that useful. If you have any questions, as always, please get in touch. As I've said in the past, this is one of the most important and most relevant tests that people run, and so I wanted to show you how to make that happen. Next time we meet, what I'll talk about is when we have two populations, but we're using what are called matched samples. So we'll take a look at that next time. It's good to see you all, and I'll see you next time. Bye.